I'd like to tell about some efforts in computational chemistry and high-performance computing within the US Army. And it's a little bit selfish in our pragmatic approach how to reduce the time to solution with the Army-related problems. And first of all, we're grateful for HPC Advisory Council for opportunity to speak here, and Gilad and Brian for facilitating last time change, and Hinesh Amin, who swapped his slot and gave me opportunity to speak today. First of all, I'd like to introduce, my organization, some of our activity, technical motivation of our work, and spend most of the time two topics. One is about first principle molecular dynamic simulation on a Cray, mostly Cray platform, and two examples of our work, and a little bit about some GPU computing and particular Amber code on a new Condor GPU cluster at Air Force Research Lab. So our environmental lab is focused on the support of US Army mission in sustainability, and we deal with a variety of physical, chemical, and biological phenomena with explosives, toxic waste, properties of material, stuff like that. So it's pretty large variety of problems, and high-performance computing is one of the key aspects where proper experiment is not available or costly. Just to give you an idea, ERDC is a part of the so-called defense supercomputing resource centers, and currently there are 5 of them. One is in Virginia, one is Ohio, two in Mississippi, one in Hawaii. Used to be one more in Alaska. It's been shut down early this year due to the cost cuts. So, and funding to this program comes from high-performance standardization program, HPCMP, which is running almost 20 years right now, and provide a framework and support for development of high-performance computing within the Department of Defense. We currently host a couple of machines, and we heavily Cray-oriented, so it's older XT4, a couple of new XE6, and Altix SGI. Those resources may not be top 10, but still there are fantastic opportunities and fantastic computational power if used properly. And to emphasize this point, when last year top 500 list been published, it attracts unusually high attention due to the fact of these 2 Chinese machines that get a prime spot, which actually inspired a lot of discussion, and especially in lawmakers and upper executives, that the China challenge the superiority of United States in high-performance computing, and the situation has been really similar to an event that took place 50 years ago called Sputnik crisis, when the Soviet Union launched the first satellite, which actually been a great thing for science and education in the country, because the education system been overhauled. It's really improved science, technology, engineering, mathematics, and new extra money been invested, which actually lead to great scientific discoveries. But this kind of crisis is really a key turning point, which made a big impact. So we're hopeful that this rise of this machine will get some effect. And just give you one practical example. those of you who don't know, the Kraken is the largest academic petaflop machine, and this is the largest machine I have an account, so I took it as an example. We've done some statistic analyzing it, 10,000 jobs, and ask a question, what is the most popular job size? Does anyone can guess? 100 cores. Oh. And we also done some analysis, what is the limit for 50% of jobs and 90% of jobs. There's a graph, shows you number of cores and normalized frequency. Doesn't looks good, yeah. Or most of the jobs are actually in below 10,000 cores. Occasionally, it's hard to see, but you see this nice capability computing splash on full machine, 96,000 cores, and but most of jobs are below 10,000. Let's zoom in a little bit. So, the 50% of the jobs are here. It's below 120 cores. 90% of the jobs is below 1,000. And the winner is 12. It's one node job. They account 17% of all number of jobs. Think about it. It's 98,000 cores machine, and yet the most popular job size is one node. And this is not a way of high performance computing we'd like to see. So, and but it really resembles a bell curve, also called a diffusion of innovation, where really a small number of people here, innovators and early adopters who really take advantage on latest technology and development, but most of users actually hopelessly lags behind, and and a small percentage even opposed to it. So what we try to do, really push forward, the state of high performance computing, and in our research, and encourage our students and collaborators to do it. Type of software we use, it's density functional theory and connected with molecular dynamics. So there's three codes we use. Fortunately, those codes are highly developed and adapted for a large-scale parallel calculations. Due to effective FFT and the task group parallelization. There is last year it's been enhanced support for XT platform, the CP2K effective integral library. And we also coupled a Cray buffered input-output library, which really helps speed up parallel performance for smaller jobs, where you have a very small time step, and this really help to speed up the calculations. Back in 2008, done some test and optimization of the code, and see that this kind of calculation runs very efficiently, 1,000 core and more, and with newer and larger machines, scaling is even better. So this allows us achieve to do a calculation of first calculation of thermal decomposition of crystalline explosives. SIL-20, this is one of the most important high-energy materials, which is widely used in the army. And its chemistry is very complex, and it's very important to understand the sensitivity and safety of explosives, as well as get some kinetic data for combustion and explosion modeling. We started with so-called unimolecular decomposition. We run a parallel a lot of molecular dynamics trajectories to get the idea how the composition it goes through intermediate and then branch out and gets on the smaller products. And the reaction inside the crystal bulk is much more complex. And these few snapshots of the simulation, you see that under an elevated temperature, this really complex reaction takes place with a lot of different compounds. Such calculations with a different temperature, we can get a concentration and time-dependent behavior, get a reaction rate, and this is really very important information to get predictive models. Our current project is focused on silicon nanowires, which are of key importance of nanoelectronics. And to give you an example, they used in field effect transistors and chemical and biological sensors, where actually the silicon nanowires put here, and the absorption biological or chemical agents adsorb. You get a difference in conductivity or change in some other properties, and you get a signal. Also used as a photodetectors. It's been nanowires put here. And of course the solar energy conversion and storage devices. All these very important applications, and experiment on such nano-sized object is really challenging. So again, we apply DFT-based molecular dynamics to get idea what are the properties, physical, mechanical properties under the load. And this figure gets you a cross-sectional view of the nanowires. Start from a very small one, a few angstrom width, to a 2.5 nanometer thick wires. And we simulate exactly the type of experiment is done, called a tensile test, where the nanowires pull out and the stress and strain measured. It gives you classic strain stress course. We apply strain, and again, and then the nanowires breaks down. And analyze some properties. Then we found those type of calculation at the ab initio levels are really computationally demanding. So until that time, most of the work been done using a classical force field and reactive potentials. But what we found then in a small nanometer range, depending on the cut of the sample, tetrahedral or octahedral, they split and behave differently depending on the type of the cut. This is really where the quantum mechanics play its role, because when you use a force field, all your atoms are the same, and all molecular or classical potentials give you one single behavior regardless of the type of the surface. And this is due to the fact that such behavior, because on a surface of the nanowire, you get a passivation. So the property of the surface layer are different, fundamentally different from the core. And when the tension is applied, those two layers behave differently. And such properties can be described only applying methods of quantum chemistry, not classical potentials. And this graph give you idea. This imaging those images from the experiment and how it's done, and those are snapshots from our simulation. There's a quick movie show you as we pull the nanowire apart, the stress is rising. And breaks down. And this is calculated curve, this experiment. What is encouraging, we get correct behavior of the strain, but the value of the stress a little bit different. But when you see what kind of objects we deal as represent the ideal cuts, and those kind of objects are very difficult to get the experiment, and in actual experiment the silicon is oxidized. There is a lot of defects, which inspire us to write a review to analyze the sources of the difference, and within the theory experiment at the nanoscale there is a deviation due to the model limitation, and under experimental conditions it's really difficult to get control the surface, so it's always native oxide, some defects or deposition, as well as some induced equipment errors. But with more and more advanced computing, the quality of the simulation model is getting better and better. Now let me switch gears a little bit and talk about the GPU. And when this year top 500 list been published, one may see that 4 out of 10 systems are now GPU or hybrid computing based. So we can say that really GPUs is very convenient, and this might be a way for a supercomputing at our age of austerity. And just recently, a GPU cluster been deployed within DoD. It's called Condor. Has a 78 nodes. It's 2 Teslas, 250 and 270. It's 156 GPU total. There's a second part of the machine using a Cell PlayStation engine. The total performance is about half petaflop. It's really nice machine, but in our work we use so far only a GPU part. And we ported and test and optimize the Amber GPU code, the latest build from August. And just briefly summarize a couple of technical challenges to achieve this. Have to use the latest CUDA 4, and the nature of the Amber code is that try different flavors, MPI and higher state and BPH. It's one that actually works so far, and open MPI actually hands it. You will not be able to run any parallel multi-GPU simulation. I found that the cluster built using T-logic of InfiniBand, and to get proper GPU direct, it's very sensitive to a type of a driver, and GPU direct is really a key technology. Gives you improved MPI scaling, and we also believe that everyone should put memory CO, gives you extra 10%. And it's a line of the code you can do that. So what you can achieve? Done some benchmarks. So TRPKH is a standard small protein with a folding time of about 4 microseconds. You can do 370 nanoseconds a day on a single Tesla. It gets 11 days to achieve brute force holding time. And in the previous talk, you heard about Intel 9 domain. So we've done some tests, and from which it's fantastic publications of folding the protein, and the folding time is 1.5 milliseconds. On a single node with 2 GPUs, we can achieve 150 nanoseconds a day. So there's no way to do a folding straightforward brute force dynamic, but if accelerated technique applied, like replica exchange with 64 replicas, this 1.5 millisecond can be achieved within a month. And the type of work we do is interaction of nanotubes and nanorods with DNA, and that is a great concern that the nanotubes are toxic and can induce DNA damage and the nanotubes are part of the various nanocomposites used in not only ZAR but various other applications. So, but the size of the system goes well beyond a 100,000 atoms. This particular one, in the explicit Holvet box, it's about 300,000 atoms. And on a single GPU, it's about 1.5 nanoseconds a day, and 8 nanoseconds a day. And to wrap up, I just like to leave you with a couple of take-home messages. First, that really systematic joint efforts between developers and supercomputing staff and user community is needed to use our resources really efficiently. And the scientists really have to match a job type size with a proper hardware and software. And this is really essential point which we have to think. And finally, to acknowledge our management team at ERDC, our IT personnel, and a lot of people who contribute to this work, to this DSRC computation allocation and NSF exceed allocation partner. Thank you very much for your attention.